Welcome back to our series on applied regression analysis. I'm Mark Ledbetter. This is lecture video 36. We are in chapter 14, Diagnostics. This is part 3. So in our last video, we looked at how to detect outliers using 6 different methods by analyzing residuals. And I strongly suggest that you write down these 6 methods, how they're calculated, and the general rules for when they've been violated, and put that together in one place, and that will make diagnostics much easier, and it will make the final exam a lot easier as well. So no hint there on what's on the final exam. So this time, in this video, we will be looking at assessing the normality, linearity, linearity, homoscedasticity, and independence assumptions using graphical analysis of the residuals. Then we will also assess normality and look at some of these alternate strategies. So let's look at these residual plots here, and these are plots of residuals. There's ordinary, studentized, or jackknife is fine, versus the predicted values, y hat. And these are useful for checking these regression assumptions. So while we can't do it with the individual, we can look at some of the individual plots, this is taking the whole model into consideration. So part A here, we're looking at jackknife residuals in this case, and remember that's leaving one out each time. And we don't see any trends. The randomness around the line at 0 is what we're looking for, so this is basically a perfectly satisfies the model assumptions. Now in plot B here, we have, of course, a departure from normality, and we may need to do a transformation since this is not linear. All right. Now in plot C here, we see that the variance is not constant, that we have across the predicted values, we have an increasing variance. So we violated the homogeneity or homoscedasticity assumption there. And finally, we have D, which is a plot across time. And here we see, because we see this positive trend across time, we have violated we may have violated independence. We probably have. So we could either include time as a covariant, and that may correct this independence, or there's some other simple solutions that we could do. But if they don't work, then what we would have to do is use something like time series analysis, and that is much more complicated. But it may be required when we see a dependence on time. Okay. So now we're looking at apply the jackknife residuals versus the predicted value of weight, WGT, in our example. And we only have 12 observations. If you look at the line, I've tried to draw a line pretty close to 0 here, that for the most part we see some randomness around that, but we do have this one part that appears to be relatively larger than the rest, and it may be an outlier. And I think we identified some of these points in the last analysis. Okay, so now we're going to try to assess normality. And normality is one of the more difficult assumptions to test at times, and let's look at why. So we can check the normality assumption by examining skewness and kurtosis, and we can use normality plots or histograms of residuals, but I will warn you that is difficult with small numbers like we have. So there are also goodness of fits tests. Some of these include the Kolmogorov-Smirnov test, the Shapiro-Wilks test, and etc. But these should be for reference only. So we should not solely base our decision on these goodness of fit tests. It's not recommended. These tests are way too sensitive. So even slight departures from normality will cause these tests to fail. Instead, there are t-tests and f-tests that are known to be robust against mild departures from the normality assumption, and you will always have some mild departure from normality, even in the best of situations, because data is varying and we don't have that perfect normal distribution. All right, so skewness, we would really want skewness to be around 0, and kurtosis should be around 3, And we see that both of these are higher, so we see some evidence of departure from normality just looking at those. And this is for the jackknife residual here. Okay, so now in the Proc Univariate from the SAS output, we see these tests for normality, and they've given 4 of them, and I want to point out that all 4 fail for normality. It says, because the null hypothesis is that data or the residuals are normally distributed. So that would be the null hypothesis. P-value is way less than 5. P is less than 0.05, I'm sorry. So that means we reject H0 in favor of HA, which says they're not normally distributed. So these tests are failing quite a bit. And we don't really use the rest of this output. This is a different normality plot than what we want. Now here's a histogram of the residuals. And this is jackknife residuals. Looks nothing like a normal distribution. You've got these points over here, so that are far away from the rest. Very difficult. So instead, we will plot a studentized residual without the current observation. And if we try to draw a line through the majority of the points here, we want a straight line. And so maybe something along here would be okay. I missed most of them. But even moving this up, it's hard to use a protractor on an iPad, I will admit. So if we do that, then we see a little trailing, if that's the right line, which I doubt it is, then we will see a trailing off here, which we normally do see that around the tails. Extreme observations are hard to make them comply with the precise normal distribution. But this point up here is quite far away from the rest of the points and may be an issue, but there's only one of them. And if we only have one, then, and the rest of these are fairly close to a straight line, then this suggests that we have an acceptable level of normality. But that one point is what's responsible for making all of these tests here fail. So that's how sensitive those tests are. Just one outlier can ruin all of them. Okay. So now let's talk about some alternate strategies for analysis. We've already talked about transformations. So if we have transformation, we want to, we have data that needs to be transformed, then we saw that in Chapter 5, and we saw that again in Chapter 6 and on our project, how we could use these transformations to correct for linearity. So now these are some constant, so we may want to do the transformation for more than one reason. Stabilize the variance of a dependent variable. So when we did our transformation on our project, we took data that basically looked kind of like this, and we made it normal. But when we plotted this data, we noticed that we had a violation of the homogeneity of variance, or the homoskedasticity. And so if we wanted to correct that variance, then we could take the log or something of either the dependent or the independent variable. We had already taken the inverse log of the dependent variable y, and so what will help correct that would be taking the log of x. And if we took the log of x, then that helps stabilize it, but it does make the analysis more complex. And then we could normalize the dependent variable. What do we mean by normalize? We could use the transform z equals x minus mu over sigma and try to normalize it, make all of the variables have a mean of 0 and a variance of 1. We could also linearize the regression model. We can transform either the dependent or the independent variables again. So linearize means, if we don't have a straight line, we have something looking like that, then we want to take a transformation. So here are some common transformations. Log transformation. So, and here in statistics, when we say log, we mean the natural log, unless we say a specific base. So we would have to specify log 10. So here we actually mean the natural log. The square root, I had you look at the square root. We also have the reciprocal, the square transformation, and then we have the arcsine transformation as well. So these can work in different situations. All right. So now let's take a look at these nonlinear regression patterns with a constant error variance and variance error and simple transformations, what we call simple transformations of X. So here we have this as a prototype regression pattern. So if our pattern looks like this, we may take the log of X. I had you take the inverse log of Y, but it may have been better for us to have taken the log of X or the square root of X. Okay? And so that may have been a better transformation for our project than what we did. And if we have a pattern that's increasing like this, then again we want to take this looks like a square. So if we were transforming Y, we could take the square root. But since if we want to transform X, then, and these are all transformations of X, then we could take the square, or we could take the X and e to the X as our transformation. A pattern like this, if we're transforming X, we could take the reciprocal of X or the negative exponent. So e to the negative X might flatten this out or straighten this out. Okay? What if we have something here where we see a change in variance that's increasing, decreasing, or and nonlinear? We have nonlinear, we have again nonlinear decreasing, and we have linear increasing. So we could, in this case, we should take transformations on Y, square root, log base 10, or 1 over Y. Okay, and it says a simultaneous transformation of X may also be helpful or necessary. Okay, all right. So let's talk quickly about a concept called weighted least squares, and we're not going to really do much with this method because of the matrix algebra and calculus required. So for this class, I just want to go over in general. If you understand matrices, you may understand this, but I just want to give you the concept more than anything. So the weighted least squared method is a way to modify our standard regression when the assumption of homogeneity or equal variance doesn't hold. So this is for variance violations, or violations of equal variance. Okay, so if we suppose that yi is known or can be estimated reliably, can be estimated reliably, to be sigma I squared divided by equals sigma squared divided by some weight wi, where wi is the weight of the ith observation. Sigma squared may be known or not known. So we're going to estimate the coefficient in the regression equation by minimizing this expression here, where we're multiplying a weight times the square of the residual. Okay, and so we could, by squaring this and working it out, we get this, and we get this expression, and we're going to let W be a diagonal matrix where the weights are along the diagonal. If we differentiate with respect to each of the beta i's, then we end up with an equation in matrix form of here. And we can solve for the parameter, and when we solve for this parameter, we call it beta hat. So we can solve for those, and we see that we end up with x prime wx in quantity inverse, and then x prime wy. So this doesn't cancel out. We have a y over here. So the variance-covariance matrix of beta hat, we can find, we actually take this variance, and if we had been looking at the matrix representations this whole time, it would be fairly obvious that this is sigma squared times the matrix out in front. So we get sigma squared, and then the x prime wx quantity inverse. And so the tests, the t-test and the f-test still apply just like the regular least squares method. And so this is one of the ways by applying these weights that we can correct for variance violations. And they call this a simple solution, but figuring out what the weight should be is sometimes a lot of trial and error or experience working with these types of violations. So here's a summary of our alternative approaches. If unequal variances, known unequal variances, then we should use the weighted least squares method if possible. If our surface is nonlinear, then we can transform the variables, or we can use nonlinear regression, or something called smoothing methods that we have not talked about in this class. And if the response variable is non-normal, for a continuous case, we can use something called bootstrapping, or robust regression, or rank analysis. Again, we're not going to have time to talk about these in this class, but I want you to know that they are available and that there's something that you could look up and learn how to apply. And then for the discrete case, we have categorical data analysis. So there are whole courses on categorical data analysis, and we could use some of those alternate analysis if we don't have a normal relation or normal variable, or if we don't have normality for each value of x. Okay, so that covers what we're going to cover right now in Chapter 14, Diagnostics. So please don't forget to scan your lecture notes by midnight of the date listed in the course calendar. If you have questions, come to virtual office hours. I'm happy to help you, or you can email me, but I need two things from you. One is a picture of your work so I can see how you're approaching the problem, and two is a picture of the actual question or problem that you're working on. And those two things will help me answer you quickly by email. I hope you will take care of yourself and stay safe. We hope to see you next time.